Hi, it's time for the math. Easy solution. We're going to discuss integrals and volumes and basically go over an introduction where we're going to define volumes using integrals. Basically, before we get to that, I just want to quickly go over these basic shapes to show you just how volumes are defined. If you had this half cylinder over here, as you can see, if it has a cross-sectional area that's uniform where it's A, across and the height's H, the volume is just defined as area times height there, A times H. And in this case, you have a circular cylinder, so with the radius R and the height H, and again, these areas are the same top and bottom. So that's just going to be A, and the area is equal to pi R squared. And then again, same thing, V equals pi R squared times H, or A times H. And now if you have a rectangular prism like this, where it's height L, height H, length L, and width W, the area could be seen as just this bottom one here, length times width. So that's just going to be area, and then the volume is just length times width times height, or area times height. Yeah, so as you can see, for these basic shapes, that the volume's all defined similarly. But now, what about general non-basic shapes, such as this one right here, where just a random shape, kind of looks like a loaf of bread, with area here at the left side A of A, that's where A here, and then the right side A of B, that's over at this area like that. And now to define a volume for any general shape, what we are going to do is something similar to our definition of area using integrals, and we're going to basically take a slice of this, kind of like a slice of a loaf of bread, perpendicular slice across it. Yeah, so at this point X, call this X right here, draw it across. This is just going to be dashed lines, meaning it's through it, and then etc. like that. Yeah, so when we draw it perpendicular across it, we're going to have a cross section, kind of looks something like this, just a random shape. Draw dashed lines through it and highlight it all across. So here's this random shape we cut across. We'll call this area now A of X. So that's it. A of X is A of A at the endpoints, A of B. There's a random side right there. Yeah, so now if I just copy and paste the shape over here, and now what we're going to do is something again similar to definition of area. So again, I'll call this now XI, this point, and I'll move left and right of this area by delta X. Right, I'll call this side delta X, and we'll use this exact same area here, this cross section at X at XI, what we're going to call, and shift it over, so left and right. So again, we're going to draw this across, and again through it, and this is going to be like this. Yeah, this side across it, this is going to be actually, I'll shift it over, so it's going to be left and right of it, so it's a bit hard to see right now, but just bear in mind. So we're going to have now the same shape moved left and right, and now we could, if we were to fill this all in, so fill this area completely in, and this volume, we're going to have a estimated volume for this segment, which we'll call VI, and that equals to A of XI times it by, well, delta X right here, which is this delta X. And now this is similar to exactly how our cylinders were initially, where you have an area times by a height, and that's our volume. So now this delta X similar to our H, so that's our H, and there's just the area as our cross-sectional area. Yeah, so now if we were to basically break up this, do the exact same thing but for the rest of the shape, and break it up into separate volumes, all with a delta X width, something that kind of looks like this, where the center of this part right here is going to be A, or we'll call this X1 equals A. Now this part right here is X2, this is X3, this is our X4, now we have an X5 right here. This is just roughly how the shape kind of looks like when we break them to volumes. is x6, and this is just equal to b right here. And now yeah, basically they're all separated by delta x. So the volume right here is roughly going to be equal to the summation of every individual volume segment. So we'll call this, yeah, this is going to be summation from I equals to 1, or sigma I equals 1. We'll call this up to n just for general, but in this case it's n is equal to 6 right here. And then this is going to be area of xi times it by delta x. So we're just going to sum this all up. And now basically, as you can see, if we were to make an infinite amount of volume segments all separated by infinitely small delta x, then that becomes closer and closer to the answer. But as you go to infinity, that is the exact answer, and that could be used as our definition of volume. So our definition goes just a limit now volume is equal to limit as n approaches infinity of this same summation up top, I equals 1 up to n of a xi delta x right here. Now this is just a Riemann sum, and like I showed in my earlier video, you could write this as an integral, and this is actually a definition of an integral. So it's integral now from a to b of a of x, which is just the which is a cross-sectional area at any point x, times by d of x right here. Yeah, where d of x is just infinitely small segment here, delta x. So it's just going to be the difference of delta x, but infinitely small. And so this is our definition of volume. Yeah, and now an important note on this definition, this definition does not depend on the shape's relative distance from the x or y axis. And what I mean by that is, if you were to draw, let's say something like this is the x and y axis, if you were to solve for the volume of a sphere somewhere situated around the origin like this, say that's a sphere, and you were to calculating it, it does not matter if the shape was here relative to the x-axis, or if it's somewhere like over here. So if these are the exact same shape, you'll get the exact same answer. It doesn't matter where it is around the x-axis. Yeah, and now just one more note. We'll consider the basic half-cylinder shape from above to show you how you could solve the area, where the area is defined as area times h right here. This cross-sectional area is the same throughout the shape, and we'll solve this exactly using our definition to show it's the same thing. So as you can see, this area, when we look at the integral right here, volume is equal to, well, from a to b. We'll write this side right here as a, and this b, and as you can see, this is a of x times by dx. Now this a of x for this shape, because a is constant, a of x equals to a, and that equals to a constant, yeah, just a constant number. So it's a constant number, so this integral can be solved easily. We'll take the a out, an integral of just dx, that is just x. Now this is from a to b, and this equals to a times it by, well, b minus a. And if the axis is something like this, where that's x going up, b minus a, that's just going to be the difference, or the difference between the two, which is just a height. So it just equals a times h. Let's write this a bit better, ah. And that is the exact same thing we have here, just to show you that it works for basic shapes. And if you have a constant area, the area just becomes constant. Yeah, and the a of x function just constant. Anyways, that's all for today. Hopefully you learned from this video. And yeah, like always, you can download these notes in the link below. And also, I'm going to go over some examples in later videos. Anyways, thanks for watching, and stay tuned for another Math Easy solution.